Today, we're going to decode the ultimate chemical cheat sheet. Seriously, this thing is like a predictive map for pretty much every substance in the known universe. And we're going to use it to solve a very, very tasty mystery.
Okay, so let's just dive right in with a real head-scratcher. How do two incredibly dangerous ingredients team up to create something so ordinary, something so essential as table salt? How does that even work?
So, on the one hand, you've got sodium. This stuff is a soft metal that's so reactive it literally explodes if it touches water. And on the other hand, chlorine, a poisonous gas. Not exactly things you'd want to have around.
But then, something wild happens. When these two get together, they create sodium chloride. You know, the harmless little white crystals we sprinkle on our fries every single day. The transformation is it's incredible.
Now, this isn't some kind of magic trick, it is pure chemistry. And the secret to how this all happens is written right into the structure of the periodic table itself. It's the key that unlocks how everything around us is made.
So let's just zoom out for a second and look at the big picture here, and what makes this table so incredibly powerful. You gotta think of it less like a boring chart and more like a predictive map for the entire universe.
The whole thing is organized by one simple but honestly really profound rule. It's called the modern periodic law. And all it really means is that everything about an element, how it looks, how it acts, is all determined by its atomic number. That's it. That number is just the count of protons in its core, and it's what gives an element its whole identity.
So here's a good way to think about it. An element's location, its address on this map, tells you almost everything you need to know about its personality and exactly how it's going to behave. And it's actually pretty simple to read. The rows tell you how many shells of electrons an atom has, kind of like the layers of an onion. But the columns, the columns are the real secret. Elements in the same column are like a family. They all have the exact same number of electrons in their outermost layer, which means they act in really, really similar ways. And this is why that location is so darn important. It all comes down to these little guys, the valence electrons. Think of them as the social butterflies of the atomic world. They're the ones on the outer edge that go out, interact with other atoms, and form all the chemical bonds.
Okay, so now that we know the layout of the map, let's talk about the rules of the road. Because the table isn't just organized, it's absolutely full of predictable patterns or trends.
You can basically split the whole table into two teams. Over on the left, you've got the metals. They're the generous donors. They just love to give away their electrons. And on the right, you've got the non-metals. They are the greedy takers. They're always looking to snatch electrons from other atoms.
And this right here is where the table's predictive power really shines. As you move across or down, properties change in a really predictable way. So for example, electronegativity, which is just a fancy word for how greedy an atom is for electrons, gets stronger as you move from left to right. But at the same time, atoms actually get bigger as you move down a column, which makes them more willing to give up those outer electrons.
For instance, just look at that first group. As you go down that column from lithium all the way down to cesium, the metallic character just gets stronger and stronger. That means cesium is even more desperate to give away its one outer electron than sodium is. See? This predictability, that is the table's superpower.
So you might be asking, why do atoms even bother giving and taking and sharing electrons in the first place? Well, it's not random at all. It all comes down to a single, universal goal that pretty much every element shares.
And the magic number is 8.
Yeah, you see, every atom's deepest desire is to have a full outer shell with 8 electrons, just like the super chill, stable, noble gases way over on the far right of the table. They don't react with anything, they're the atomic role models everybody wants to be like.
So let's get back to our salt mystery. Sodium, our generous donor, has one lonely little electron it's dying to get rid of. Chlorine, our greedy taker, has 7, and it desperately needs just one more to be happy. So sodium just gives its electron over to chlorine. Bam! Now they both have a stable outer shell, they become charged ions, and that opposite charge holds them together in a super strong bond. Mystery solved.
And that simple act, that little exchange of trading or sharing electrons, that's the basis for every single substance you've ever seen or touched. And the specific strategy an atom uses determines what the final compound is going to be like. You've basically got two main game plans here. There are ionic bonds, like we saw with salt, where there's a complete transfer of electrons between a metal and a nonmetal. And then there are covalent bonds, where nonmetals decide it's better to cooperate and just share electrons instead.
And these different strategies create compounds with totally different personalities. Ionic compounds, like salt, they're hard, crystalline solids. They have high melting points, and they conduct electricity in water. Covalent compounds, on the other hand, are often liquids or gases, have low melting points, and don't conduct electricity at all.
So, what this all means is that the periodic table is so much more than just a poster you see in a science classroom. It's a powerful user's guide to the entire universe. It lets us predict how the fundamental building blocks of matter are going to combine to create, well, literally everything around us. The same rules that explain table salt, they explain it all. So the only question left is, what will you decode next?